we will be happy to have them on board later in the session. I'll share my screen. You can turn off your cameras, which will improve the audio quality as well as it will not distract others. Arpit, you can turn off your camera. Okay, so welcome to Chem Club. Chem Club is a process design engineering and advanced software solution consultancy. It is an ISO 9001-2005 certified, and it is run by highly professional chemical engineers having industrial experience as well as professional knowledge. Services offered are basic engineering and field studies, wherein the project team does the basic engineering and the detail engineering for the projects, then process modeling and simulation for upcoming projects as well as the existing processes, process monitoring and troubleshooting services, advanced software solutions, wherein you can have digital twins and process monitoring, wherein you can improve the productivity by monitoring parameters. I request everyone to please mute your mics. This is really disturbing for everyone. The training services offered by Chem Club are simulation and modeling in Aspen HYSYS, simulation and modeling in Aspen Plus, advanced process engineering, process control, PSV sizing, HYSYS, sustainability training, heat exchanger design during using Aspen EDR, process design in detail engineering, distillation column design, and chemical process safety. We are having software licenses of many of these softwares, and you will get authenticated results for all your technical queries, right? So I'll start with the presentation for which we have gathered today, which is on fire and explosion concept and prevention. So when we talk about chemical industry, fire is one of the major cause of many big incidents, which have caused many fatalities, property damage, losses to environment, and has caused legal troubles for many organizations. Today, we are going to understand what exactly are the causes of fire and explosion, what is the difference between fire and explosion, and the preventive measures that we need to consider to prevent such incidents. So let's get started. First of all, what is fire? To be really fundamental, it is a chemical reaction. It is a combustion process wherein the material is converted to byproducts, which are say oxidation products of that reaction, mostly converted to CO2 because carbon is contained in most of the chemicals, and when it is oxidized, it converts to CO2, releasing a lot of heat, which again causes damage in terms of burning of the material and causing burn injuries to the people who are exposed to it. The fires are not all same. So you might have seen different types of fire. Sometimes you might have seen tanks burning in videos. Sometimes you might have heard explosions. You might have seen tanks getting kind of ruptured, exploded. So and sometimes even a jet of fire coming out of a pressurized piping. So all these fires are different in one way or other. So the categorization is flash fire, pool fires, and jet fires. So what are flash fires? Flash fires are those which occur when the liquids give off vapors, get an ignition source, and the vapor is ignited, vapors are ignited, and there is a localized fire. We call it as flash fire. In case of pool fire, it occurs in liquids when a liquid is spread across surface and it forms a pool. The liquid is above its splash point, it gives off vapors, and those vapors when get ignited, the entire pool of liquid catches fire, and the fuel under the fire is supplying continuously because there is a lot of fuel in that. So the time for flash fire is basically some seconds, but pool fire can think that it can run for a longer period of time. And why is it important? Because when flash fire takes place, the equipment under fire is impacted. But when there is a pool fire, it is an extensive area, and that the radiations from pool fire can actually damage the structures. And when the structures are impacted, uh, there will be uh, there will be additional materials which can come out from the tanks which are getting impacted, and thus getting additional fuel. And these
Sir, you are on mute.
Hello, hello, am I audible?
Yes.
Yes,
Yes,
sir.
sir.
Yes.
You are
Yes,
audible.
sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So you didn't hear anything till now?
No, we were hearing that after the flash fire and the pool fire.
Oh, okay. So till what was audible? The difference between flash fire and pool fire?
Yeah,
Yes,
we
yes.
got to know that.
Okay. So basically, flash fires are less dangerous than pool fires because of the extent of damage it can cause. In pool fires, if you have a pool of liquid which is continuously giving fuel to the fire, it increases the severity because it collapses the structures containing other flammable materials, and those contents add to the fire, and then the fire basically spreads, causing additional damages. And in jet fires, it is basically a pressurized stream of vapors which are flammable in nature, which are coming out from, say, piping or a pressurized vessel from a gasket, which are ignited, and then you can see a jet of a fire getting out of the vessel. Now when this jet comes out, it is containing a lot of heat, lot of energy, because it is having a lot high velocity as well as heat. So impingement or impact of this jet on another structure or another equipment is really dangerous, because it can give the similar effect that of a gas cutter. So you might have seen gas cutters are used for cutting the metallic structures. So these jet fires do the same with the structures they are exposed to. So in a nutshell, uh, flash fires are less dangerous, though not, you can say, you cannot say that they are not hazardous, but they are less dangerous compared to pool fires and jet fires. Then what is an explosion? So explosion is an after effect of fire in terms of a pressure wave. And the difference between fire and explosion is, when something is burning, it is burning at certain rate. But in explosion, that rate is very, very high. So
Sir, you're not audible.
getting, I don't know whether somebody's muting me. Okay, so rate of energy released is very high in case of explosion and compared to fire. And in case of explosion, actually confinement is the key. So if you have flammable vapors or the substance which is combustible in nature, and if it is confined from all sides and then it is ignited, then it can convert from fire to explosion and cause a lot of damage, because it is having a higher energy. One of the unit is basically heat release per unit time, so that is very high in case of explosions. And because of that, pressure waves are generated, which actually ruptures the equipment which is holding the flammable material. And the pressure wave also disturbs or destructs the structure surrounding that equipment, and which is again causes the domino effect. Then maybe you guys are aware about fire triangle, wherein I hope my screen is visible, right?
Yes, sir,
Yes.
your screen is visible.
Yes,
Yes, sir.
sir.
Okay.
Visible. Is it
Okay.
possible? It will be better, sir. Can you put in PPT mode, sir?
I'm not putting in PPT mode because I'm not able to see when it is muted. Then somebody of you have to take the responsibility that once it is muted, somebody will give a shout out. Is it okay with you?
Yes, sir.
Okay, sir.
Okay.
No issue.
That is
Okay.
possible.
Okay.
Fine, fine.
Okay.
वरती बस.
Okay then. So the fire triangle consists of heat, oxygen, and fuel. So this, please mute now. I'm not able to see whose mic is going on. So everybody should mute themselves. Okay. Thanks. So the fuel in this case can be solid, liquid, or gas. Solid like wood, paper at your home can burn. Gasoline, diesel, methanol, benzene are the examples of liquid fuels, and gases like hydrogen, acetylene can burn. And those all are examples of fuel. If you consider ability of fuel to catch fire, then gases are more sensitive, and the parameter which determines this is called minimum ignition energy. So if you compare minimum ignition energy for gases, for liquids, and for solids, for solid it is quite high. For liquids it is sometimes in between 1 to 3 millijoule, or sometimes it is above 3 millijoule. For gases it is extremely low. For liquids also it is sometimes less than 1 millijoule. For gases it is extremely low. It is said that a simple single static charge can ignite hydrogen.
Sir, again you are in mute.
Sir, you are not audible. Please open your mic.
Sir, you are not audible, sir. Please.
I'm not sure why it is happening, but thanks again. Is it visible and audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Thanks.
Yes, sir.
So
Sir, is it possible that the admin can only change the mute and unmute?
I'm not sure right now, but we will think about it in the next maybe session.
Yeah, please show
Yeah,
that
thanks.
admin can process that mute and unmute for
Got
all
you.
the
Sir, this is
participants.
happened in frequent training session like this only.
Okay. Thank you for the suggestion. We'll definitely take care of it next time. Yeah. So fire is desired in some cases. For example, we cook meal at home using fire, and we run boilers using fire. So it is not that fire is always undesired, but we don't want fire when we don't want it. So when we don't want fire, we have to remove one of the three constituent, either oxygen, heat, or fuel from it to extinguish it. So when there is a fire, you might have seen people rushing with say fire extinguisher. What they are doing, depending on the type of extinguisher, they are removing either oxygen or heat. So if you are using water, you are actually removing heat. When you are using chemicals like CO2 or say foam, then you are basically covering the surface of the fuel so that the atmospheric oxygen do not come in contact with that fuel, and the fire is stopped. So this is basically breaking the fire triangle to collapse the fire or to stop the fire. And this is true for all the chemical plants which we are running, and there is always a possibility of fire because of presence of flammable chemicals. And some chemicals are above their say flash points, and because of that they are in the flammable range. So the only option that is remaining is oxygen. Also they need a ignition source along with heat. So we have to control either oxygen or ignition source to prevent fires from happening. Now how do we do that? Let us check it ahead. So why heat is a component in fire triangle? So heat, you can think of heat in two sense. One heat is responsible for heating the material to a temperature wherein the vapors are sufficient so that it is ignited. You might be aware about the concept of flash point. It is a temperature above which the material can ignite, below which the fire doesn't take place. So some heat is required to the shift the material from its non-ignitable zone or non-flammable zone to the flammable zone. And even when the liquid is above its flash point, it will not catch fire automatically. It will again need some ignition source, and that is also possible through heat, right? And those ignition sources we are going to discuss in detail in the upcoming slide. The next component is fuel itself. So the material which is getting burnt is basically the fuel. This can be, as we discuss, a solid, liquid, or gas, right? Third component is oxygen. So as we started the presentation with the statement that fire is basically a combustion reaction which needs carbon and oxygen. Carbon is present in fuel and oxygen is supplied through atmospheric air. So in case if we remove oxygen, there will be no fire. So this is what we do to prevent fires from happening. Now the relationship between various properties. You can see on the x-axis there is a temperature called flash point temperature. It is the temperature above which the liquid gives off sufficient vapors so that it can be ignited when there is a ignition source. And you farther right you can see auto ignition temperature. It is the temperature at
So
which
your video is off. Video is off. We can't see the screen.
So the screen is not
The
visible,
screen.
sir.
yeah, I got it. I'll have to fix it actually. Let me know once it is visible. Is it visible now?
Now is it visible, sir? Yeah.
Okay.
Now
Sir,
it
now
is
now we can't
visible.
see.
Okay. Maybe I'll keep it in this mode so that I can see it. Okay. So
Okay, sir.
yeah. So as you can see on the left hand side, it is flash point, and right hand side is auto ignition temperature. So auto ignition temperature is basically a temperature wherein you do not require any ignition source. It will ignite on its own. And this temperature is quite higher compared to flash point. So for example, temperatures of solvents, the flash point temperature of solvent might be less than even room temperature, but their auto ignition temperatures are of the order of 250 or 300 or 400 degrees centigrade. So there are two aspects to it. When the material is above flash point, we have to prevent it from getting the ignition source, and we have to make sure that we don't get an ignition source which can cause a temperature higher than auto ignition temperature, which is taken care by means of temperature class of equipment. So for example, there is a substance having say auto ignition temperature of 200 degrees centigrade. So we cannot use an electrical apparatus or instrument which is having a temperature class which can give a temperature in case of failure above 200 degrees centigrade. Otherwise, that material will catch fire. So this we will be seeing in our detailed course wherein we will discuss all those technical terminologies of temperature class, gas group, so and so forth, and how the motors, how the electrical apparatus, how the instruments are selected for certain gas groups, what are the temperature classes, how they are differentiated, that we will be seeing in our upcoming series of lectures. Now coming back to this diagram, you can see that there is a limit called lower flammability limit. So there is a line connecting flash point to lower flammability limit. It means that at flash point temperature, the lower flammability limit of the material is reached. So the concentration is such that the material is giving off sufficient vapors so that it can be
The
ignited.
screen is not visible. Screen is not.
Sir,
Sir,
it's visible, sir.
I thought it is visible.
Sir,
It is
not
visible
visible.
now?
Yes.
we can able to
Yes, sir,
see,
it
sir.
is visible.
Yes,
Okay.
visible. Visible, visible.
Okay, okay,
Yes, sir, it's visible, sir.
okay. So when the temperature is above flash point, it is in the flammable range, and when it is below the flash point, then it is in the non-flammable range. That is how the temperature or heat plays a role in case of um, fire triangle. So we come to know that if we want to uh, prevent fire, we'll have to store the material or operate or handle the material at a temperature less than flash point, so that we can also allow ignition sources to take place. But is it always possible? It's a question to all of you. Is it always possible to handle the chemicals below its flash point?
No.
Yeah, because they are quite low and you might require them to be handled at elevated temperatures for say reaction, for distillation, for separation, extraction, any of the operation. And so we cannot take credit of flash point, or we cannot rely upon flash point always to prevent fires. So what do we do when the temperature is above flash point and we still have to use it? How do we prevent fire in that case? So I guess I explained all these terminologies to you except fire point. Fire point is the lowest temperature above which the vapor will catch fire and it will sustain the fire. It is basically a higher point compared to flash point. We actually never rely on fire point for safety purposes. We always prevent flash point. Or if the material is above flash point, below fire point, we still consider it as flammable because we do not always have control on the ignition sources. Okay. Okay, so let us understand the difference between detonation and deflagration. So when there is a fire and subsequently an explosion, this flame front or the flame of fire can transmit in either slow or fast, depending upon various properties of chemicals, geometry of the place where the reaction has, where the fire has started, and based on that, uh, the explosion can be divided into two parts, which is deflagration and detonation. So deflagration is the fire or explosion wherein the flame propagation speed is lower than that of sound. So it is in the subsonic region. And in case of detonation, the speed of flame front is higher than the speed of sound. So, but obviously detonation is more dangerous because it is the flame front is running at a very high speed. So the fire is propagating at a very high speed. The gases which are generated because of the fire, they are traveling at a very high velocity, which will create a pressure wave, and it will damage the structures. So this image shows you the difference between detonation and deflagration. So the black one is reaction front, basically where the fire is taking place, and the gray one is basically the shock front, or you can say the wave location. So in detonation, the reaction front is very close to the shock front, and in deflagration, reaction front is far behind the shock front. Because of that, you can, as you can see in the graphs, you might be seeing that peak overpressure or the overpressure because of the fire in both the cases or explosion in both the cases is same, but the rate of pressure rise in case of the first case is quite high. If you can see, the peak is very sharp. So the distance at which this occurs, it will get a lot of pressure suddenly. So you can call it as dp by dt, rate of pressure change per unit time, is very high in case of detonation, which creates impact on the structures and it damages the structure, causing a lot of damage. Whereas in deflagration, though the peak overpressure is same, it will not impact the structures that much as compared to detonation. So can deflagration convert to detonation? Yes. How it can convert? When deflagration is going on, there is it is not a really stable thing, kind of a bike running on the road. It is not something like a bike running on the road. It is kind of a, you can say, jet plane cruising in the sky. So it is traveling already at a very high velocity. So if it is if it gets some geometry wherein the speed will increase, the flame propagation will increase because of, say, confinement, because of the pipe diameters, lower pipe diameters, then the deflagration can convert to detonation, and then the damage would be higher. Now, why it is important for us to know whether the flame or the fire will cause a deflagration or detonation? This is relevant when we choose flame arresters type. So there are certain flame arresters which prevent only deflagration, and there are certain flame arresters which prevent detonation as well. So whenever we are selecting flame arresters, we should be aware what kind of pressure rating it should have. Otherwise, if we select the flame arrestor for deflagration case and detonation occurs, that flame arrestor itself will get damaged, and it will not do its job of preventing the flame from coming into the reactor. Now, what are the ignition sources that are responsible for fire? So as we talked about fire triangle, we talked about oxygen, fuel, and ignition sources, or heat. So heat is given in terms of ignition sources. These ignition sources are hot surfaces. Now the examples of hot surfaces are, say, hot pan. You might have seen in laboratory that they use this a pan which is provided with the electrical heater. It gets hot. You might have used in college or your organization as well in lab. So this hot surface, if it gets contact with a flammable vapor, and the temperature of hot plate is higher than the auto ignition temperature of your fuel, then this can cause a fire. And these hot surfaces are also possible in case of hot works like cutting or welding in plants. So these can cause fires if they get a flammable atmosphere around them. That is why when we do hot work, we ensure that there are no flammable vapors surrounding the area. Can somebody share what is the test that we do when we do hot work in the plant? What we check? What do we check? Anyone? Somebody raised a hand some time ago.
Sir, I have one question for hot surface ignition.
Okay.
Is it mandatory to catch fire when the auto ignition temperature is reached,
Yes,
or
that is
fire point is reached due to the hot surfaces?
no. In case of fire point, you will need an ignition source. In case of auto ignition temperature, you will not need an ignition source. Is it clear?
So you want to say that if the fire will occur due to the contact of flammable vapor or mist due to the contact of hot surfaces, it must catch it the temperature of auto ignition temperature.
Right, right.
Okay,
Because
okay.
if you go by the definition, it's a very good question. If you go by the definition of fire point, it is the temperature at which the fire will sustain, right? Sustain
Yes, yes.
when you get a ignition source. So ignition source is also required. But in case of auto ignition temperature, you do not need additional ignition source. That is why we refer to both the terminologies differently, right? And because source
Got
is
it.
required in flash point as well as fire point, as a additional safeguard, we consider flash point because it is a lower value to safeguard our processes compared to fire point. Okay, good question, by the way. Thanks.
Okay. Thank you.
Yeah, I guess hot surfaces are clear with everybody then. Then we come to static discharges. Now, these are the notorious ignition sources which are very tough to control. This can happen
So
because
please,
of,
so you have asked a question. Uh, Can we get the answer of that? That what we check when the hot work is done?
yeah, I expect somebody from you to answer it actually.
Yeah, lower explosivity limit, LEL.
Yes.
LEL.
So that is the minimum concentration, and it should not Yes, it should not be the case that the space is having flammable vapors and still we are going with the hot work. That is the reason we check LEL, so that we do not get a fire when we are doing hot work. Okay. So for static discharges, the static discharges are charges. Just give me a minute. Okay, sorry. So static discharges are the ignition sources which are omnipresent. These are the discharges. These are the ignition sources which are very tough to control. So this can happen because even with a simple friction, as you might have all experienced the experiment of chair being rubbed against a cloth, and because of that, the person sitting on the chair, if you touch him, then there will be a spark, right? There is a precondition involved wherein you do not get this spark. Can somebody tell me that condition?
Can you repeat, sir, and question?
You might have experienced the static charges, or you can say sparks, when you might have sit on a chair and somebody would hit that chair with a cloth. We used to play in our childhood that somebody used to sit on a chair, we would hit that chair with certain cloth, and then if we touch that person, then there will be a spark. Have you done it?
Yes.
In that case, the contact must be there.
So there are
Chair.
three conditions, preconditions, which are required for this experiment to be successful. Yes, Pratik. So in that experiment, the person needs to keep his leg off the ground, right? Why is it required?
Otherwise, all the charges would, yeah, due to the grounding, all the charges would go into the earth
Yes.
or in the ground.
Yes. So that is one precondition, that the person should keep his legs above the ground so that the charges don't pass on to the ground. There is another condition with respect to the material of construction of the chair. Can somebody share
Chair,
that?
chair is not electric conducting.
It
Not
should not be
conducting.
the insulator.
It should not be insulator, or should be insulator?
Should be insulator, I think.
Should be
Correct.
not conductor, sir.
Not conductor. Yeah, one and the same thing, that it should not conduct. So basically the charges should not get earth, and only then this experiment is successful. Now when somebody touches that person, what actually happens? Can somebody share that? Why he gets that tingling sensation? Why that?
It creates sparks.
Why that spark is created?
The static charges flow through the another person who touches the sitting person.
And why they should go to the person?
Due to friction.
Free from of electrons.
Free flow of electrons. Right?
Because there is a different charges on both the objects. One has other charge and other has different charge.
Okay, so maybe all of you know the reason. I'll just put it in the maybe technically correct words. So when the person touches him, he is actually grounded. So he is in contact with ground, and electrical charges always try to earth themselves. They want to find a conductor which can take them to the ground. When the person is sitting on the chair, all the chair legs are plastic. There is no way of the for the charges to go to the ground. So when the person touches the person sitting on the chair, the charges jump on that person and they try to find a path. And if he is grounded, they pass through him and get grounded. And that is the path of electrons, and that is why he feels that electricity. Electricity is basically flow of electrons. So those electrons pass from that person sitting on the chair to the person standing, and then through him it reaches ground. And that is how the charges flow. And because of those charge jump from the person sitting to the person standing, there is a spark, right? And if you don't touch the finger, if you put a palm on him, then you might not actually get a spark, because it needs a sharp object to get those charge jumping. The area should be less, so that the motion of electrons is sudden, as well as it is kind of restricted, so that it is converted to a spark. So this is how static discharges occur, and these are relevant ignition sources even in case of plant processes. So if you have say ignitable material or a flammable atmosphere around that discharge, then that material can get ignited. Chandramouli has raised his hand. I think we will just finish the lecture. We are quite ahead of time. We will have a lot of questions after the session. Don't worry about it. Yeah, so in plants, when you are handling chemicals which are not conductive in nature, so chemicals like toluene or xylene or benzene, they have a property that they do not conduct the charge, like the person sitting on the chair, because the chair did not pass the charge; it was accumulated on the person. So because of the material of nature of the material of these substances, the charge gets accumulated on them. Now when they will get it, when they will discharge it in terms of a ignition source, so whenever they get a conductor which is connected to ground, they will discharge it, and a similar spark which you felt during touching the person sitting on the chair will occur, and that is called as static discharge. So there is a difference between static generation and static discharge. Static generation occurs because of the friction. So when the material is getting charged inside the reactor, or it is flowing through pipes, because of friction it accumulates the charge. When it gets a conductor, the charges jump on that conductor and gets earth. In the process of it, there is a ignition, or there is a jumping of charges which causes an ignition, which can cause fire if the flammable material is present there. I hope the point is clear. Then there are mechanically generated sparks. This you can think about wherein you are hitting a metal with another metal, or if you drop a heavy metal object on another metal object, you can see that there is ignition, or there are sparks. These sparks are capable of igniting flammable vapors, and thus they should be prevented. Then the next is electrical apparatus. So in case of electrical apparatus, if they get short circuited, or if there is overheating because of excessive current, they will get heated. And in case of short circuiting, there will be release of electrons which are similar to that of a ignition source, and this can cause actually ignition if the flammable atmosphere is present. Lightning is a very classic example, wherein in monsoon, when there is thundering, after that if the lightning occurs and it reaches any ignition source, it can cause fire. You might have seen that lightning has caused many trees to burn. So this can happen, that these lightning would land on a tank of a flammable material and it can catch ignition. I will come to the safeguards which are provided to prevent fires because of each of the ignition sources within the same slide, just after completing the how these ignition sources work. Then there is self-glowing. So this is basically a property of a few powders or say solids, wherein when they are exposed to certain conditions, some oxidizers or some energies or some initial ignition, they start to glow. So they basically burn, but without any flame or without giving off much heat. So you might have seen wool getting burned. So this is glowing. So if the wool is on fire, it will not kind of create a big flame, but it will burn by itself, and it is also an ignition source. So if there are metal wires are a good example of self-glowing. So if there are such ignition sources present in the plant, they can ignite the flammable atmosphere. The next example is adiabatic compression. If you are compressing a gas, the temperature of it will increase. We know that when the pressure increases, the temperature increases for an ideal gas as well as for other gases, but the relation is somewhat different. So when there is a compression, the temperature of the gas will increase, and this increased temperature can actually cause the temperature to go above auto ignition temperature, and thus causing ignition and then fire. This generally occurs when you compress gases like liquefied nitrogen gas or certain petroleum gases to fill in the cylinder. You have to take care that you cool them sufficiently once you compress them, so that they are not in the flammable region. Sometimes they use a technology of multi-stage compression. So they will compress once, let it increase by a certain degree, which is safe enough, then cool it again, then compress again, then cool it again, that kind of methodology. So this is also an ignition source, which is not really common in chemical industry. And the next one is ionizing radiations. That is also not really common. These are basically radiation causing fires. I guess none of the chemical industry is having such installation which is giving off radiations that can cause fire. Okay. Now, how will you control these ignition sources? So for hot surfaces, we use equipments with the temperature class, so that even in case of failure, the temperatures do not exceed the auto ignition temperatures of possible chemicals. So for example, there is a plant, and we are using certain chemical having a temperature class T4, and it is having a auto ignition temperature of say 200 degrees centigrade. So we will sorry, it is having a T4 equipment will have a failure temperature. So the temperature which it can go up to is 200 degrees centigrade. So we will have to make sure that plant do not have any material which is having a auto ignition temperature of lower than 200 degrees centigrade. So basically we have to ensure that even in case of a electrical malfunction, that electrical apparatus will go to a temperature which is less than auto ignition temperature of material being used in the plant. This is how we prevent electrical apparatus generated hot surfaces. Other things that you take care is hot work permits, wherein you ensure, because in that case you cannot eliminate the ignition source, you ensure that fuel is not there. That is how you take care for the hot surfaces. Then for static discharges, uh, there are certain technical measures to reduce the impact of static discharges. One, as we discussed, is earthing, wherein we provide a metallic path for the charges to discharge from equipment to ground, so that they do not accumulate and create a discharge causing fire. In case of glass lined reactors, we provide tantalum tips, or we also provide uh, flanges or gaskets with conductive nature, so that the material in contact with it can discharge its charges. So these are the constructional measures which we take for preventing static accumulation. Then we try to reduce velocity. We ensure that velocity is low when we are charging a flammable liquid. We use dip pipes to prevent splashing. So these are the methods through which we ensure that the static discharges do not occur. We also provide earthing and bonding on piping, so that the piping is always electrically grounded, and even if there is a static charge generation, which is always going to happen, those charges are grounded safely. Then there are mechanically generated sparks, which we talked about. If we drop a heavy metal object, or if we hammer something, there is a choking in the plant and you need to kind of hammer the pipe with a hammer, then you can have this mechanically generated spark. uh, Can somebody share me which tools are used in plants so that you do not get mechanically generated spark?
It is non-sparking tools.
Non-sparking tools.
Brass
Somebody
tools.
said
Non-sparking
brass.
tools.
Yes.
Brass,
So
brass.
brass, correct. Brass is softer in nature. So it is whenever it falls down, it do not give off mechanically generated spark. Right. That is why it is preferred choice whenever there is high probability that ignition, the flammable atmosphere will be present inside a plant, and we always keep in mind that we do not provide ignition source. And to prevent ignition sources, we use these brass tools so that we don't provide ignition sources. Then electrical apparatus, we talked about temperature classes. It is basically a bit lengthy topic to cover in a short period of time. So we will be covering it later. Lightning, we have talked about that we can have lightning, we don't have a control on it. Okay, only nature and God have control where and how the lightning will occur. So to prevent our assets, our chemicals from lightning, we generally install lightning arrestor. So you might have seen a structure, kind of a star shaped structure at the top of your unit, which is connected to earth. So whenever there is a lightning, it will first try to reach any earthing point. As we discussed, that charges always try to ground themselves. So it is at the top of the plant, so that the if it is traveling in the direction of plant, the the lightning arrestor will catch it and ground it safely. So the preventive maintenance of that lightning arrestor, the earthing, bonding and conductivity of those strips connected to lightning arrestor are really required, and they are checked in the preventive maintenance schedule of the plant. I think other examples I already given, that wire mesh can self glow, and adiabatic compression of uh, those hydrocarbon vapors can actually be an ignition source. Okay, so let us go to BLEVE. So what is BLEVE? The full form is boiling liquid expanding vapor explosion, and this is something is also not in our hand. So whenever there is a fire outside, say a reactor wherein solvent vapors are filled in, a solvent is filled in, solvent as in say toluene is filled in. So when the reactor is getting heated from the outside, the toluene will get heated, and it will reach a point wherein the tank will be pressurized. But because there is increase in pressure inside the tank, the remaining liquid toluene will not boil off, but it will be at a temperature above its atmospheric boiling point. Because of the pressure under which it is stored, it will not boil inside, but it will remain in the liquid state. In case there is a leakage from say bottom wall, or a flange which is located in the bottom area of the tank, in the lower area of the tank or reactor, then there will be a leakage, which is basically toluene at a temperature above its boiling point, but it is in the liquid state because of the pressure. So when it comes out of that leakage, it will basically convert into gas, and because of that, the point at which it converts, it comes into the atmospheric pressure, it will expand, and because of that it will exert a lot of pressure on the flange it is leaking through. So it will kind of a blast, it will kind of expand exponentially, it will expand to its vapor state from the liquid suddenly, and this is basically called as BLEVE, which is boiling liquid expanding vapor explosion. Is it clear to everyone, or shall I tell it again? Because this is a complex thing to understand. If somebody is having a doubt,
Please,
they can ask again.
please repeat it again, sir.
Okay, I understood it rightly. So please listen to me very carefully. If you are also looking at something else, you will not understand this concept for sure. Okay, you need
Please
to.
give
Take
one or
one
two
simple
practical
example.
examples.
I got two voices. Can you repeat?
So please give one or two practical example of it, uh, like on a daily basis or day-to-day life,
No, no, no.
so
Blavy do
that we
not
can
occur on
relate.
daily basis. Blavy do not occur on daily basis. You might have seen videos of it wherein you just see a leak at first and then suddenly the tank gets exploded. That is a Blavy, right? But these are not really frequent cases because of its inherent requirements. So I'll repeat the sequence again. Assume there is a tank with a closed vent. Let us assume the vent is closed and there is say toluene filled inside the tank. Okay, and now there is a pool fire. Pool fire is basically the tank is on the ground floor and the ground is having a material, say toluene from another tank has leaked and it has accumulated there and now it is ignited. Now those flames are causing the tank to heat. The storage tank containing toluene with the vent closed is getting heated. Now the toluene in the vapor phase, the toluene will try to convert to vapors, right? So it will convert some liquid to vapor state. Now once that liquid is converted to vapor state, it will cause pressure to rise inside that tank, and because of that pressure some liquid will stay inside the tank as liquid because it is not the boiling point is elevated when there is an increase in pressure. So water boils at 100 degree at atmospheric pressure, but if you pressurize the water to say 10 bar gauge, the boiling point will not be 100, it will be higher, say maybe 180 or 190 degree centigrade. So when you increase the pressure, the boiling point increases and the material stays in the liquid state. So in this case, the fuel, the toluene will remain in the liquid state. Now because of the heat or because of the pressure generated, there might be a small leakage in the reactor, which is getting pressurized. So once that leakage occurs, the material which is coming out, if it is in the bottom of the reactor, the liquid filled part of the reactor, the material will come out as a liquid, but when it comes just outside the reactor, it will be exposed to the atmospheric pressure. Earlier it was exposed to the pressure in the reactor. So from 10 bar gauge to atmospheric, it will suddenly expand, and because of that action of expansion, that crack will widen, right? And that will cause the entire equipment to fail. That is basically the Blavy, because once the crack widens, more liquid will come out and this phenomena will repeat itself. And once the crack is wide enough, a lot of liquid which is above its boiling point will come out and it will kind of expand, and it will start to expand inside the reactor also because the pressure has gone down because of the leakage now, and that will cause the equipment to fail, equipment to rupture, and kind of blast away. So that is basically Blavy. It is called boiling liquid expanding vapor explosion. Okay, maybe you will have to check it once after the session as well, so that the concept is clear with you. Okay, so what do we do to prevent explosion? We remove one of the three components, right? So one of the method to remove one of the three component is to remove oxygen. So we replace oxygen with nitrogen. Nitrogen is having inherent property that it does not burn and it does not support combustion. So there are various methods of inertization wherein we bring the limiting oxygen concentration below the uh, we bring the oxygen concentration inside the system below the limiting oxygen concentration. Now what is this limiting oxygen concentration? It is the concentration below which the fire does not propagate in particular material. It is a material specific property. So LOC for toluene, or limiting oxygen concentration for toluene, will be different from methanol or that of benzene. So it is basically a chemical specific property. It has been tested in the laboratory for this particular property. So they try to reduce the oxygen and still try to ignite it. And at a concentration below which it is not ignited, it is called at its LOC, right? And to take additional safety margin, we generally go 50% of LOC. So for example, if there is a chemical having LOC of 8%, we ensure that the concentration of that, the oxygen concentration inside that reactor is below 4%, not 8, to be very sure, to account for any errors, right? So how do we do that? We do it by means of either vacuum purging, wherein we pull out entire air from the system and then release nitrogen inside it, and again pull out the air and again release nitrogen inside it. So this is called as vacuum purging. Reverse of it is pressure purging, wherein we put nitrogen inside the system, pressurize the system, vent it to atmosphere, again pressurize the system with nitrogen and vent it to the atmosphere. Both these systems can be used to remove oxygen from inside the system, and there are equations from which you can calculate how much cycles are required both for pressure and for vacuum to bring the concentration of oxygen below certain concentration. So for example, if you want to bring the concentration below 4% from 21%, how many cycles of nitrogen pressurization you will need? That also varies with pressure. So higher the pressure of nitrogen, lower the cycles are required, and lower the pressures, higher the cycles are required. There are equations associated with that, and we have also the template wherein you can calculate the cycles required for your particular case, your particular chemical, as well as your pressure of utility, that is nitrogen, and you can then use it to safely inertize your system before you actually put in chemicals or take that particular material for say preventive maintenance or any hot work. Okay, this is for the pressure purging. Now, how do we design the explosions by static electricity? So we just discussed those things when we were discussing related to static charges. We have to control the generation because static electricity is everywhere. So you cannot eliminate it by, like you can eliminate oxygen by means of nitrogen. You cannot eliminate static electricity. However, you can reduce it, reduce the impact and reduce the time for which it is generated. So how do you reduce the generation of static electricity? By reduction of velocity. So for example, if you are charging a drum and you are charging it for a flammable material, then what you can do, you can reduce the filling rate for that particular material. Also, you can dip the filling pipe deep inside the drum so that the splashing do not occur. So these are basically reduction in velocity and turbulence. This is how you control the generation. And in the same drum, if you connect a conductor, you can call it as crocodile clamp or something, and you connect it to the metallic part of it and then connect it to the ground, then you are allowing the charge to generate, but then dissipating it also as well. So the accumulation do not occur. If it is not accumulating, if it is getting conducted through the crocodile clamp, then there is no problem. One thing that you need to take care is, do not try to dissipate the charge once it has generated. So for example, if you have a drum and you have started filling it, and if it is now having sufficient material and it is above its splash point, say for example solvent like benzene is filled in that. Now if you try to attach a crocodile clamp now, then there are charges on the drum which will jump when the crocodile clamp is getting very close to the drum, and if the vapors are present in that area, then there will be ignition. So you need to ensure that the clamping, the earthing has to be connected before the drum filling has started. So these are really very minor details, but really important when it is the case for the prevention by means of static discharges. So that's it for now from this webinar, and I look forward to the questions now. Thank you. Yes, Mangesh. Am I audible? Am I still audible?
Yes, yes, sir.
Yes, sir.
Yes, sir,
Okay.
you are audible.
So those who are having question can raise their hands. I think I will be able to see them. Satyajit.
Yes, sir. So I have the question.
Hmm.
Like I said, I think what is the engineering control to avoid the static electricity? It is a very common. So like
Hmm.
as you said, the velocity, it is a very calculation. So 1.5 meter per second just to have to calculate.
Hmm.
And if we are not, what are the second layer or third layer to avoid to be provide the control measure? Like as the second said, the deep pipe.
Hmm.
So another, what are the measures to be provided to engineering control as not a part of administrative control? What are the engineering control will be best to avoid the static electricity?
Okay. So for static electricity, as you shared, a reduction in velocity is one option. Earthing and bonding is the second option, and if dip pipe is the third option. So this is sufficient to reduce the static electricity. In case of tankers, so if you have tankers which are containing flammable materials, relaxation time is also calculated, because in that case you might have to take samples, or you might have to connect that spool piece with the tanker and then allow the material to come down. So relaxation time is also one measure which is used. Now in terms of technical measures, if you inertize the system, Jay, you can close your camera. Yeah. In case you inertize the systems, then some static discharges are not effective. So there is a paper wherein it was researched that if you if you reduce the oxygen concentration available, the MIE will increase, and the static charges like static discharges due to friction are not an effective ignition source. So if you are having an inertization, you actually need not to worry about static charges that much. So that is the best engineering control that you can provide. Nitrogen
Uh,
inertization.
yes, sir. Now, like as a we have a design some plant. So like we have provided like 1.5 meter per velocity. Like we have calculated the 1.5 times to avoid the static electricity. In
Mhm.
point of the second layer, we have provided J type charging also. J type.
Okay. Is
Okay.
it is the tank nitrogen inertized?
Now, yeah, that's the issue. So we have no any provision for the nitrogens. We have no any utility of nitrogen.
Okay.
So we cannot check the like LOC limiting of oxygen. So is it required for everything? Like as we handling the solvents and monomers. So is it required and is it compulsory?
Is it
Yeah, like for the
yeah,
for
you
the
need.
refineries, they're mandatory like continuous braking.
No, see,
Is it
technically, or you can, if you go by fundamentally, there is no difference between a refinery and a chemical plant. So hazard remains the same as long as the properties remain the same. So if your material is really, you can say, sensitive to ignition, yeah, if the MI is quite low, then you actually need to put nitrogen inertization as a really inherently safe safeguard. Otherwise, as you said, J pipe is a good safeguard, but in that case you are relying more on earthing and bonding, right? So you need to ensure that those are really in very good shape, so that the even though there is a charge generation, it is dissipated very easily. Okay, there are plants which are running without inertization. They are handling solvents, but they are making sure that the other safeguards are really good. And in case of the
thank you,
velocity, as
sir.
you said,
Uh,
you can provide deep pipe and a slow filling. Okay, so you can start slowly, so that till the time dip pipe is filled, you are not allowing the velocity to go above 1 meter per second. And after that, you can increase the velocity. That is a good option.
okay.
Yeah.
Thank you, sir. Last is the like if this is the option after addition of the all the solvents. If I plan the also powder like charging,
Mhm.
so that is also chances the static also. So
Yes.
that is we have a provide administrative controls like in liner bags, everything. Just to as you said, the like arctic crocodiles.
Mhm. So the
Okay,
powder you are
but that
charging,
is a human error
correct. So the
chances.
powder you are
Sorry,
charging,
sir.
you the powder you are charging, you need to check the MIE of that powder, minimum ignition energy for
Okay.
that powder. If it is say highly combustible, if the MIE is quite low, and then you need to actually have anti-static bags as well. Also, the MIE for hybrid mixture is quite low. So when you are charging powder in a solvent, you are actually creating a hybrid mixture in the vapor space. So you need to take care more compared to solvent, pure solvent. So hybrid mixtures are even more sensitive than pure solvents. You can think of other options like can you charge powder first and then solvent if the powder is readily soluble, to make it inherently safe, that in the empty reactor you will charge the powder directly and after that you will add solvent. You can think of such options to make the design inherently safer.
Okay,
Okay.
just will check. Thank you,
Yeah,
sir. And I hope, sir, regarding we'll make a training session HAC hazardous area classification. It will be more better for us.
definitely.
Thank you, sir.
uh, I can see more hands.
Hi, sir. This is Sarvesh from. Sir, I work in an aviation industry. So there we have a tank farm area, and we
Mhm.
have a fuelers filled with the ATF.
Okay.
So coming on the static charges, we check the conductivity on the daily basis.
Mm-hmm.
So we have a provision that the conductivity should be in between 50 to 600. What are the consequences if it goes below the 50 or it goes above the 600?
So
How it
what
can
is what
affect?
is yeah, what is the unit of this 50 and 600?
Because I'm in per meter.
Picosiemens per meter, 50 to
Yeah,
100. Yeah,
50 to 600.
50 to 600
Yeah,
picos.
yeah. We daily check the conductivity of that material.
Okay. I'm
Uh,
not sure about the aviation standards as I am from a chemical background, but let me tell you something fundamental. If you have a higher resistance, so a higher conductivity means lower resistance, and a lower conductivity means higher resistance, right? So if you go below, so if you are checking conductivity and if you are highly conductive, then there is no need to worry. So if you are checking conductivity and if it is sorry, the resistivity, and if it is less than 50, then there is no problem. If the conductivity higher, resistivity is lower, then there is no problem. In case of increase in resistivity and decrease in, that is conductivity, you will face problems. The static charge will face problems to go to ground, and the accumulation of charge will increase. So from certain experiments, they have derived the standard values of resistance at each level, for each, you can say, type of installation. So if there is a reference already available for you that you need to keep it below that value in terms of resistivity, you need to do that, right? But
yes,
above
sir.
is not a problem. So more conductive is definitely not a problem.
Okay, sir.
Yeah.
Thank you, sir.
Okay.
Good evening, sir.
Good evening.
Sir, myself Mohit, still a student who is entering next month in third year, sir.
Mm-hmm. Good to see you here.
Sir, sir, I am very interested in taking a process design or a chemical process like that, sir. Can you try to make webinar on that, sir?
Uh, as in, you want to be a process engineer? That's what you want to say?
Yes, sir.
Okay, so for that, there are certain courses even provided by Chem Club, or uh, by Chem Club, there are certain courses which can train you for uh, becoming a good process design engineer. One fundamental requirement from, as you are a college student, you need to have a good fundamental knowledge about all the basic subjects like fluid mechanics, heat transfer, mass transfer, uh, So those are core subjects, the fundamentals of which should be known to you, and then you can build upon that with the help of this additional kind of calculations, additional knowledge and expertise, and then you can become a good process design engineer.
Sir, I'm planning to take the course from next month, sir, because our fourth sem exams are currently going on.
You
So
can
I
you can
left taking the course.
you can do it earlier, not a problem, but make sure that you understand it, because if the content requires you to know the basic. For example, somebody says that Reynolds number, the flow in the heat exchanger shall be turbulent for a better heat transfer. You should know what is Reynolds number, what Reynolds number is required for the flow to be in the turbulent region. Then only that statement will make sense to you. That is what my message was.
Okay, sir. Okay, thank you, sir. Sir, last one request, sir. What you have showed us the presentation, sir, PPT. Can you share in the group, or can you share who are registered for this? Can you share them personally, sir?
I'll
It's a
check
request.
with the team. I'll check with the team actually. Yeah, we'll try to do that.
Thank you, sir. Thank you for valuable time.
Yeah. Welcome. Yeah, I still see few hands raised.
Good evening, sir.
Good evening.
Sir, can you tell us the difference between earthing and bonding?
Yeah, very good question. So when you say earthing, you actually mean that you are connecting something to earth. The name itself suggests. So for assume there is a piping which is composed of 5 pieces, right? So one piece is connected to other by means of a flange, and there is a gasket in between, right? And you have connected one conductor to earth the charges from the fifth pipe to the ground, right? Now how will the charges from first pipe to will go to the second one, second to the third, and so on. So for that you need to connect all the pieces of piping with each other apart from the flange, because there is a gasket in between, by a jumper. So there is a connection from one pipe or one flange to other flange by means of a metallic jumper, which is called bonding. So that is basically the difference between earthing and bonding.
Two flanges are connected by nut bolt. Can charge travel by nut bolt?
Yes, so if you see, the nut bolt surface is not really a smooth one, and sometimes there is grease present when the nut bolts are inserted. Also, the contact area, if you might have actually seen the flange in the field, the contact area between nut bolt and the flange is very small, and those can also get corroded. So there are multiple factors by because of which the conductivity of the nut bolt is not always possible, and that is the reason, as an additional safeguard, we ensure that okay, this is a clear cut path for the charges to flow. We do not rely on the nut bolts only, but yes, technically they also carry some charge. You may have a case wherein if you do practical example and you measure the resistance across a flange, you might get a very less resistance, which means that the nut bolts are actually conducting the charge, and you actually don't need the jumper. But this can be a case, there can be a case wherein this is not happening, and to be on the safer side, we actually provide additional bonding apart from the nut bolts.
Thank you, sir.
Sir, my question is, sir, in like in recent cases, many industry are having the cooling line as a PPRCT line or HDP piping, but that cooling water is going into a heat exchanger, which is having a flammable material. So my question is, like when we are connecting that polymer piping with the metallic, like heat exchangers are metallic only. So I also want to know about the static charge between the polymer piping and between the metallic. So is there any cases like a cooling water, it is a conductive? So like is there any concerns with polymer with metallic connections, or like there should we also provide the jumpers? Just asking this question.
Yeah, good question actually. But if you see, fundamentally, we are not mixing water with the chemical directly. So the water side of heat exchanger or the utility is already non-flammable. So even if there are static charges, then there is no problem as such. If you think fundamentally. Now, in case for a hypothetical scenario, even if I assume that it is going to a flammable region, once it gets in contact with the metallic part, it will start to give away the charge. And the property of water is as such that it is not a substance which will hold the charge. It is conductive in nature, so it will not accumulate the charge. So once it comes in contact with metallic part, it is
Metallic
going to give
slime.
away the charge. Yeah.
Okay, okay. So not that much big risk, or we can say that, right?
If you are using it as a utility, then no risk at all because you don't have a flammable
Of course,
atmosphere.
yes.
Yeah.
Yeah, yeah. Okay, okay, got it, sir. One more question, sir. Initially, you told about detonation and deflagration. So I want to know, like, detonation, like you convey one message that about the velocity is important, like sound velocity, Mach number. But I also want to know in terms of process, like if it is an end of line, like we are installing at the end point. Example, like a PSV vent. So we normally have the PSV vent and we install at 4 meter the flame arrestor. So it is normally a venting, like pressurization, or what is the case would be popping up. So my question is that, like at the case of the venting, so what should we prefer, deflagration or detonation, flame arrestor type?
So in this case, actually, this assessment is done based on the distance of ignition source from the point of release. So what is the ignition source that you are considering? Because in process there is no ignition source. You
Actually,
are considering.
yeah, actually, sir, yeah. Example, I am saying about the buffer vessel of hydrogen vessel. Example, if we are installing on that vessel, sir, which I understood from the vendor is that the flame arrestor, when we install, if the fire is inside the tank or is inside the before the flame arrestor, then that flame arrestor is would itself melt out, or would itself would not sustain that
Correct.
hydrogen fire, correct? So in that case, they were suggesting like use deflagration type, like it's the end of line, use at the outlet of the PSV, and install it at a 6 meter. So overall, simply went like
Then what is the purpose?
item, and they are recommending like you simply use end of line deflagration, because hydrogen fire, none of any of these devices will sustain. They simply say this type of sentence. So,
Okay.
like in your initial technical round, I understood like detonation is much better, but like in the practicality cases, people are governing through like the case to case or fluid type decisions.
Yeah, it is not necessary that everybody will have same knowledge and understanding of every technology.
हम मराठी में
Sometimes
बता रहे
if they
थे,
do not
हम
have
मराठी में,
certain model, they
मराठी या
might sell
गुजराती
you
में,
something
सब
which
एक
they
ही
have.
है।
That is a different topic, and I don't want to go into that. And also for hydrogen, if you are considering fire already inside, then what is it that flame arrestor is going to protect? That is the question that if we need to ask to ourselves, that if we are considering fire is already inside the say venting vessel.
No, no, sir. Actually, the started why we started the discussion, like PSV cases, like fire is there, or from that cases it is the outlet of the PSV. So all of the like best selection we were also trying to have. In that case, we took all cases, like what should be the best considerations.
Okay, and
Like no one should later stage ask you have selected a wrong product.
okay. Okay, maybe it is quite complex to explain right away. Maybe you can drop your query to Chem Club, and we will get in touch over this with detailed kind
Okay,
of properties as well as the installation details.
okay, okay.
Sir, can I answer this question? Because I just recently, conducted a session with the Protigo. You can ask this question Protigo also. They are very, German company. They are installing this flame arresters especially.
Okay, maybe
I just got one
let us
information
Mudra,
that
let us do one thing. you to note each other's name, search each other on LinkedIn and talk, because we are actually waiting for others to ask their question. It's a good initiative by you, Motilal, that you want to answer his query. I would suggest you to connect with each other on LinkedIn so that you can discuss. If you have additional questions, you can connect to Chem Club on official mail ID. Thank you. Yes, still some hands are raised.
Good evening, sir. Hello.
Yes.
Sir, my question is that during the hot work permit, we measure the LEL only by gas detector. But why we cannot measure the UL of that particular solvent or material? Always we measure or we check the LEL of that particular material. Okay. So in gas
Right.
detector it's mentioned, but why UL is not checked or mentioned in that method?
So if you see LEL and UL of various chemicals, you can see that there is a big gap, and UL is very much higher compared to LEL. So in case there is a concentration which is, say, above LEL, you would actually know it by smell for many chemicals. Right, that is one thing. And second thing is, you don't want the chemical to be in open atmosphere. So it is expected that there will not be a release. So in case of a small leakage or small kind of a trapped material, it will only exceed LEL and not UEL. And when you check concentration, it is giving you a value in terms of LEL. Even though the concentration is so high that it is above UEL, it is also going to sense. The meter is going to sense it. It is not like it will not sense it. If there is a substance, hypothetically, which is of a flammable nature and you cannot smell it, even though it is above UEL, LEL meter will definitely sense it.
Okay, sir.
And LEL is never a good control on any flammable property, because sorry, UL is never a good control on any chemical property, because of, say, for example, you have a reactor and a vapor pressure is so high that the vapor concentration is above UEL. But when you are transferring it by means of a pump, there will be air ingress from the vent, and the concentration will reach a region which is lower than UEL, and then you are in the flammable zone. So never go for a UEL as a safeguard, even if you are having a very high concentration of fuel inside any reactor or inside anything, because air ingress by means of vacuum, backflow, or leakages can be expected at any point in time. Yes, Pramod.
Yes, sir. Thank you so much.
Yes, Ajinkya.
Good evening, sir. I have another question. We have in our plant thermic fluid as a heating medium at 290 degrees Celsius. So our vessels are insulated by rock wool outside.
Okay.
Uh, when there is leakage in jacket, so we observe there is fire in insulation. Generally, by inherently, rock wool is not flammable, and that hot oil is not also flammable. So when we discuss this with our vendor, so they are like opinion that when uh, insulation is porous material, when uh, oil comes into contact with insulation, there is increase in surface area of that oil, and this causes the fire. So is it correct?
This has happened in many chemical industries, that firewood has caught fire because of thermic fluid leakage. And the reason is, yes, extended surface area, because when you check the properties of the material, you actually don't uh, check for you can say that particular physical density for the glass wool. But these cases have happened in industry that because of the leakage of thermic fluid oil, glass wool has caught fire. So yes, this is possible, and this is a relevant can say cause of incident. So you need to actually yeah.
What will be the reason for fire in that case?
It is glowing. We discussed in our PPT the presentation glowing as one of the cause, wherein the fragments or the filaments of a material catch fire even at a relatively lower temperature compared to their bulk material. So I am not sure whether they have tested glass wool itself or the parent material of glass wool when you are talking about the ignition temperature. But from the experience of industry, it is true that the fibrous material, the filament material, because of the extended surface area, it has caught fire. And this you can also understand from examples like when you want to start burning wood, you actually reduce the particle size. You actually start to first ignite the smaller particles of wood, and the bigger ones do not actually ignite instantaneously. So particle size is one of the aspect wherein the material's properties change. Even the ignition properties change because of the particle size. So I don't know whether the glass wool has been tested in the properties in the particle size where used in the plant. Maybe it may happen that it has been tested at say a higher particle size and given a wrong value if it is available. But yes, reduction in particle size is a cause. Small particle size is a cause that it can ignite easily, which is also true for other powders, other flammable or combustible powders as well. So particle size plays a role.
Thank you.
Are there any more questions? I can see Pramod has raised his hand, and I can see it.
Hi, sir. Sir, earlier you have mentioned about a course, sir. Can I know the detail about that course?
About?
About that course, design course.
Yeah, it is by Chem Club only. You can check the website. You, if you know the name of the webinar conducting organization, if you search by the name in the internet, you will get to know about the webinar, the course.
Okay, sir. Okay, thank you.
Okay. Yes, Senthil.
Hi, sir. Good evening.
Good evening.
Sir, I'm working for the API block. We have multiple solvents and acids and bases. Which pipe is preferable for the drainage? Either it is HDP or what type of compatibility we can search?
You have multiple streams of acid.
Solvents. Yes, multiple solvents, polar solvent, non-polar solvent, and acids, chlorine.
Chlorine?
That means chloro products.
Okay, okay. So in that case, if you want inherently safe design, I would suggest anti-static PTFE lined piping. So metallic piping lined with anti-static PTFE. So PTFE will help you to handle acidic and so corrosive materials. And because it is anti-static in nature, you will be able to handle solvents as well in the same line for inherently safe purposes.
Thank you, sir.
Okay. Yes, Ajinkya.
Sir, I have another question. In our industry, we use anti-static filter cloths for solvent filtration. So how do we check the material is filter cloth is actually anti-static?
There are tests wherein they check the conductivity per unit area. These are specialized tests and they are actually defined by standard organizations. And they are not done at say operating plants. They are done by manufacturer and they provide you the certificate of that value. So you can ask to the vendor, give me the certificate for the anti-static property or conductive property and what is the value for the cloth which we are using, and then you can cross check it with the standard that whether it is allowed for particularly your substance or not. Your vendor will
Which value, sir? Conductivity.
Conductivity value, yes, or resistivity. He might provide you either of them.
Like it is like 0.2 ohm is the standard general.
Sorry.
And resistivity standard is generally 0.2 ohm.
Yes, and for the for different materials it is different. So you can also ask vendor whether my material is so the whether your cloth is suitable for my material.
Thank you.
Yeah. So if there are no more questions, I think.
Good evening, sir.
Okay, we have another one. Okay.
Good evening, sir.
I cannot see your name actually. Just a minute. Can you tell your name?
Ravi Kumar, sir.
Yes, Ravi, please.
So please tell the believe how can be controlled only cooling method, any other methods?
Which Blavy?
Blavy.
Okay, so Blavy, you need to control your pool fire first. So because if there is a pool fire, then there is no control. And second measure is firefighting. So you have to cool the tank to a temperature lower than low as possible for sure, so that Blavy does not occur. But by design, there is no method to prevent Blavy except explosion vent or a rupture disc. So you can think about in case of a pool fire, if you don't want the Blavy, you can have a vent with installed explosion vent or a rupture disc, which if the reactor is pressurized, it will rupture and release the content. Then you will have to worry about the you can say flow of the content to a safe location, release of those material at a safe location, right? That way you can prevent Blavy. Best option is to prevent pool fire.
Okay, sir. Okay.
And one more safeguard that is possible is pacifier protection. So in case of a pool fire, they provide a pacifier protection wherein there is a coating of a material which will prevent the tank from getting heated, which will delay the heating period. That will give you more time before the Blavy actually takes place to basically evacuate. It will ultimately, the vessel is going to fail if the fire continues, but it will give you time to evacuate. That is called pacifier protection.
Pacifier protection. Okay, sir. The surge pressure create static errors, it is sir?
Sorry?
Surge pressure creates static errors, it is sir? Suppose sudden closure of walls any in the process.
Sudden closure of walls do not create it can create you can say pressure surges. Yes, it will also contribute for generation of static electricity, but that is not the only cause. A normal flow of material through piping is also responsible for generation of static discharge. For sudden closure of wall, you need to worry more about pressure surges and pipe ruptures compared to static discharges.
Yes, sir. Thank you, sir. Thank you.
Welcome.
Sir,
Yes.
sir, one question.
One by one.
Sir, is the oxygen flammable above 99% purity or above 21% purity?
I'm not sure. Why would you try to ignite oxygen? So do you mean
No, no.
oxygen itself will
Actually, no,
burn
no.
kind of thing?
Actually the context is fire and safety. So
Uh,
just I want to ask, like, we are having all scenarios with respect to air having a 21% oxygen.
right.
So, like, if oxygen is a product, so just want to be have a knowledge about oxygen fire safety
I
as a
think
gas.
oxygen do not burn to the best of my knowledge.
Okay.
It supports combustion. So if you try to ignite oxygen, I guess it will not ignite to the best of my knowledge. But I'll also have to check and to what concentration. Because if it was the case, then there would be a lot of fires in hospitals because they provide oxygen, and sometimes statics is always possible to happen. But I have not heard any case like that. So I can guess it that it's not flammable.
Okay. Okay, sir.
Yes, Mangesh.
Yes, sir, my one question.
Yes, go ahead.
Sir, I have
Sir, is
one question, sir. Sir, I have a question.
Everybody's having a question. Just let's go one by one. Priyank, maybe Priyank can start. Yeah.
yes, I asked first. Sir, is there earthing and bonding required during the diesel charging in DC generator?
What is the flash point of your diesel?
I
Haven't
need to
checked.
check, sir.
Okay. So if it is LSD or HSD, are you aware? Low speed diesel or high speed?
LSP,
It is LSD.
LSP, sir.
Yeah. So your flash point would be around 48 or 50, 48, I guess, degree centigrade. So as a rule of as a fundamental, you don't need any protection in terms of ignition source control because it is not flammable at room temperature or ambient condition. So you need not to worry about anything. But in case there is a change in composition and flashpoint has come to a temperature which is, say, close to your operating temperature or storage temperature, because it is stored in metallic drums. So to be on the safer side, as we don't know the mixture properties, because diesel is not a single component, it's a mixture. To be on the safer side, we consider diesel as flammable. We control ignition sources by earthing and bonding, and that is how we deal with diesel. Is a boundary line case, so you can always debate about it, but as it is boundary line, we consider it as flammable and treat accordingly. So yes, we provide earthing and bonding.
Okay. Thank you.
You're welcome.
Sir, can I ask one question?
Yes, please.
In our slide, there was one graph between the concentration of flammable vapor against this flash point. So we have explained the LEL and UL, it is a flammable zone, but the left hand side there is some mist is there. So is it having this mist like, you know, the sulfuric acid mist or oleum mist or any this is having any engineering controls on this for the storage tanks because it's very carcinogenic or the, you know,
No,
very
this
inhalation is
mist,
difficult.
the mist that we were
Mist.
talking about was with respect to flammable substances only. So we were not talking about other properties like corrosivity or toxicity. We were talking about only flammability. So when there is a mist, the ignition can occur at a temperature lower than the flash point as well. So that was the point in the graph, that you can rely on flash point as long as you are handling it as a liquid. So once it is mist, kind of a spray, then you need to actually take additional measures, additional safeguards, because it may happen that a substance is not flammable at a temperature when it is liquid, but when you spray it as a mist, it becomes flammable. And that is the reason why some fuels are injected as a spray when they are expected to combust. So they are injected as a spray. Maybe your car is also one example. So we inject petrol not as a liquid but as a mist, so that it ignites instantaneously.
Okay, sorry.
Okay.
But in case of some inorganic component, we are not expecting any flammable, because inorganic itself name suggests there is no any hydrocarbon present. But
I will say check flash point. If it is
okay.
below your operating temperature, you are safe. And for
Okay.
such chemicals like sulfuric acid and all, they are not flammable. That is very well known. So you also need not to check the flash point.
Okay. Yeah, thank you, sir.
You're welcome. Yes, next. I can
Sir, you
see.
were just talking about the relaxation word, one word. What does
Yeah.
that mean, sir?
So relaxation is basically allowing the charge to get discharged to earth. This is basically you can say applicable to transport vehicles. So when you are transporting solvent by means of trucks and tankers, there are a lot of potholes on roads, speed breakers, so that the liquid inside has undergone a lot of turbulence, and we discussed that because of turbulence there will be static charge accumulation. The vehicles wheels are basically uh, conductive towards conductive range, but it is not always ensured that they will always dissipate the charge. So when the tanker comes to the site, it is expected that it should be provided with certain relaxation time, so that charges will escape through the earthing which is provided. So you earth the tanker, hold it for some time, and allow the charges which are accumulated to let go through that earthing. And the time for this can also be calculated. There are certain standards for it. If you follow them, you can also check what is the relaxation time based on the geometry of the tanker and the compound that you are handling, basically on the conductivity properties of those substances.
Okay, thank you, sir.
Okay.
So in the webinar, you tell about detonation and deflagration. Can you explain more about it? How to identify the flame stage with detonation deflagration? Is
So
based on the
actually,
product?
no. It is based on the location where you want to install the flame arrestor. There are, as somebody already shared, that there are two types. One is end of line, and one is placed in line. So yeah,
Inline.
yeah. So inline and end of line. These are the two types of flame arrestor which are used. As apart from that, based on the geometry of the piping, the type of flame arrestor is decided. And I don't have that handy with me right now, otherwise I would have explained it to you, that how do you actually select that. So the properties that include the distance of ignition source from the flame arrestor. It is the main constituent of that selection criteria, but it is not possible to explain everything in this short period of time.
Okay, sir. Okay, sir.
Okay. If there are no more questions, I think time is also getting close to 2 hours. Thank you so much, everyone, for your patient listening, as well as actively asking whatever doubts you had. And I got to know a lot from you as well when through your questions, some of my concepts got revised. And I hope that webinar was helpful to you, and look forward to see you again. Thank you.
Thank you, sir.
Sir, if possible, share the PPT.
I will check that with the team so that that can be shared. Thanks.
Yes.